we go on, I would pause the screen, take a picture of the formulas that we'll be utilizing. There are 2 videos. The next video will be how to utilize if you have raw data. If you have raw data, there is a less complicated way to do it in Excel. We're going to utilize the formulas. Why? Just to truly understand what is involved in the hypothesis test for average, and we have independent samples. So let's get right to it. Well, first we need a question. And our question of the day, example 1, a 2002 study investigated the effect of background music to learning in the age group of 10 to 12-year-olds. 2 groups were built, with group 1 having no background music during the test, and the other group listening to soft music during the test. In the music group, the average on the test was 86.4 points with a sum of squares of blah. The non-music group averaged 78.8 points with a sum of squares of blah. Both groups have sample sizes of 25. SS, again, equals sum of squares. So is there evidence of a significant difference between the 2 music conditions? Well, first, we have to understand these are independent groups. Dependent groups, look at my future videos to look at the dependent groups hypothesis test of means. So these are independent groups of each other. The reason being is, to me, there's no pre-post results. To me, dependent usually means it's like a pre-post. You give somebody a drug and you look at them pre and post. You kind of study the same person, same data file, pre and post. In this case, we're looking at 2 different groups and trying to compare them. 2 distinct groups. We're not matching them together. Some people call the other version the matching group. In this case, we're not matching these people together. We just have one group and another group, and we put them together. All right. So how does one do the hypothesis test? Well, let's go through our steps of hypothesis testing. Step 1, you got to give me the hypothesis. All right. And as my formula sheet says, the typical null in this case is the difference between the groups, that is the averages of the groups, is 0. All right, the difference between the average of the groups is 0. That's the typical null hypothesis, is I believe the average is the same. Now, what are we trying to study? Well, in this question, we're trying to study, we got to read, is there a difference between the 2 music groups? Is there a difference between the 2 music groups? So we're looking to see if there is any type of difference, positive or negative, we don't care. Is there any substantial difference when we look at the averages of those groups? That's what we're testing. We're going to test the alternative to see if we get to reject or not. And so we're looking at a non-equal to test, just like you've done for 2 samples is very, very similar. So number 2, now we need your choice, critical region or your test statistic. Let's say we build the critical region first, so the critical value. Well, this distribution, for the most part, is normal. Though you might be saying, how do you know you have normal? I'm just going to assume that in this case. But how do you know you have normal? You would actually have to prove that the data you're looking at is normally distributed. All right? You would actually have to show this in real research. All right? And the reason being is our sample sizes were under 30. Since our sample sizes were under 30, I couldn't enact the central limit theorem here. So what I'd have to do is I'd have to check out each one of these distributions. I'd draw the frequency distributions, draw the histograms, draw the box plots, look at the mean and medians. There are many ways to show normal before we move on. I'm going to assume that because that's kind of a side note. The big thing here is to get through the steps of the hypothesis test. If you want to talk about showing normal, please look at one of my videos for evaluating normality. All right, so the critical value. Please, it is a 2-tailed test. How do I know that? Because of the not equals to. That's why. Now, the piece of information I am missing, and I got to go back to my question, is the question stated, is there evidence at a 5% level of significance? That is important, as you know from previous examples. The level of significance is the area outside of both bars. And that's total, that is. So since alpha, as we call it, let me write it up here, and that's usually why that's also in step 1, is what is your alpha? Since your level of significance, alpha, is 0.05, that means the total area outside will be split in two at 2.5 each. All right? And so the critical value, given that we are looking at, and let's be careful, let's go back to our formula sheet. We're looking at the t, notice the t distribution here, the t distribution. Because we're looking at the t distribution, this will be the t curve. All right, that's very important. We're looking at the t curve right here. And we got to find the degrees of freedom of this t curve to know exactly which value this is. Well, we got to be careful. This is a two-sample question. So since it's a two-sample question, the degrees of freedom will be n1 minus 1 plus n2 minus 1. We have to take the sample size of each of them, subtract off 1 for degrees of freedom of each one, and then add them together to get total degrees of freedom. It should show that up here, but I don't see that. Yep, the t-stat has degrees of freedom determined by, there you go, degrees of freedom 1 plus degrees of freedom 2. The sum of the degrees of freedom is what I'm utilizing there. So for me to find the critical value, I need to know the degrees of freedom. I need to know what t-curve we're picking on, remember. And so in this case, back to my drawing pad, I know each one had 25, so 25 minus 1 is 24, so it's 24 plus 24, which is 48 in size. So that's the t-curve I'm looking at, t-curve 48. Remember, the degrees of freedom just tells me exactly which curve I'm picking on. There's a t-curve for each degrees of freedom, and depending on the degrees of freedom, it's how close the t-curve is to the z-curve. The z-curve is the perfect curve in some respects, the normal curve. But the t-curve is very similar. That's why I drew a picture. All right, now that I know the degrees of freedom, how does one find this box? You could do it by the t-table, of course, or because we're utilizing Excel, I'm going to utilize Excel for what it's good for. The Excel does the integration, does the calculation, the nasty information. And to find this bar, just understand, critical values are always found by t inverse, t dot inverse. What does t dot inverse need? It needs the area below the bar. So we got to pause there. The area below the bar. And that blue line is a total of, well, if there's 2.5% above it, that means there's 0.975 below it. And the degrees of freedom is 48. And that's what you need. See, what Excel needs is the area below and the exact t-curve. Those two together, it'll do the calculus needed to figure out that bar, and that is the critical value. All right, that is your critical value right there. So let us find that. Let me go to Excel. And as we're doing Excel, what I would think about is how could I automate this? So if I see another question very similar, how could I automate it? Well, think about the pieces that have come into this. Think about, we're going to have probably an X bar 1 for the first group. We're going to have, it looks like we're going to have the sum of squares 1 for the first group, and we're going to have sample size N1. And then we're going to have another group, right? We're going to have X bar 2, we're going to have sum of squares 2, and we're going to have N2, all of which we can find, right? N1, read, what is the sample size of the first group? 25, because it says both groups have sample size 25. You'll need this information later, but let's check it out. What was the average of group 1? Well, you got to decide which one's group 1. Let's say group 1 is the music group, okay? Group 1 is the music group, and they got an average score of 86.4 with a sum of squares of 1550. Group 2 had an average of 78.8, so that group 2 is the one with no music, with their sum of squares being 1204. So that's the information I was given. From this information, I would like to derive everything I need. For example, the total degrees of freedom. I would like that. Well, that I can do. Just understand how you would write it. Well, look at the formula. It's N1 minus 1 plus N2 minus 1. I'm trying to automate it. So if I change anything up here, it automatically just fills in down here. This is what a person should do is, as you do in one example and you get it correct, now that you know the formulas are correct, you can just change numbers and watch that change. You know, now if this was 36, boom, degrees of freedom updates nicely as long as it's correct. And in this case, it is n1 minus 1, n2 minus 1, add those together. Let me bring back to the original sample size, 25. All right, cool. So there's the degrees of freedom. From there, we did find the critical value, right? So we need to write our code for the critical value. Well, the critical value is based on alpha. So, or it's up to you how you want to do this. You can change this as needed in here. So it's t dot inverse, and you should draw the picture and understand the 0.975. You see, this one's a little bit more complicated to automate. That's why I'm typing it in as 0.975. That's based on the alpha of 0.05. If you're clever, you should be able to understand how to go from 0.05 to the 0.975 if you understand the picture I drew. Comma, degrees of freedom. And that's the bar I was looking for. Again, for those people clever, what you could do, let me insert here. Shift, so that's going to shift that whole thing down, huh? I just realized something. I don't want to do that. I don't want to shift information in between there. But let's say over here, I gave alpha 0.05, because that's what's in this question, 5%, 0.05. Could you automate this critical value? The answer is you can. You just got to think about how that picture was drawn and how the picture will always be drawn in a two-tailed test. The key is this is a two-tailed test. And that's extremely important, a two-tailed test. If this was not a two-tailed test, you should change things to meet the one-tailed test requirements. So this is a two-tailed test. So what do we have here? So we have the critical value. 201 is my critical value. Back to my picture, 201. So what that means is if I get a data value, my test statistic, that exceeds 201, or negative 201, I'll reject the null and I'll be happy. That's the idea. If you fall in here close to 0 for the test statistic value, you will not reject. If you're over 201, you will reject, which means we need the test statistic. Well, the test statistic I'm going to do completely in Excel. How would one do it? Well, let's look at the formula sheet. The test statistic is right here. That's called the test statistic. It is mean 1 minus mean 2 minus the overall difference, which, by the way, notice we're assuming that difference is 0. Huh? We're assuming that difference is 0, so we're going to put 0 in there, over the standard error of the differential. Well, the standard error of a differential is a little complicated to find. It is this number. It is the square root of the pooled variance divided by group sizes. How do you find the pooled variance? Well, it's the weighted meaning of the sample variances, and that's right there. Notice they use the sum of squares plus sum of squares divided by the degrees of freedom added. All right, so we already have degrees of freedom 1 plus degrees of freedom 2. That's just degrees of freedom, so we already have that number. We need sum of squares added to get the pooled variance. The pooled variance is what we're going to write now. So we can call this SP2, the pooled variance. The pooled variance is what again? It is the sum of squares added divided by the degrees of freedom. Again, the pooled variance, because what we're doing is we have the variance of each group. We're going to pool them together because we're doing an independent sample. So we're going to pool the variance together when we're looking at this differential. We're going to look at the kind of weighting, averaging the variance of each one. And that's what we get. So the pooled variance is 57.375. I need to pause because I need to look at the formula. It is sum of squares 1 plus sum of squares 2. I just wanted to make sure of that. I want to make sure I had the right numbers in there. Awesome. So please notice that's SP squared. SP squared, all right? So when you plug it in, that's just a direct substitution, please. Don't square any number when you plug it in, right? SP2, I just found that. SP squared, I just found that. So if I want the standard error, and that's what I'll call it in my notes, the standard error, well, let's go through that formula. That standard error is what? It is equal to the square root of the pooled variance divided by the sample size of group 1 plus the pooled variance divided by the sample size of group 2 equals. Now let me just verify that formula one more time. I want to make sure when I type these in, it is correct. It is the square root, SQRT. It is two fractions, right? It is the pooled variance divided by group 1 size plus pooled variance divided by group 2 size. By the way, whenever you write a formula, when you double click, left click on it, you get to see how everything highlights and how it's built, so you can examine it one more time. These are complicated formulas, and so we want to make sure they are entered in correctly. The great news is, again, once you get one question right, you know you've gotten written for the most part right. You might need to tweak it every now and then. You could just then change numbers and see how everything changes with it. What I'm trying to do is have all these numbers just to adjust as I change information. So once I've written them right in Excel, I don't ever have to worry about it again. So the standard error is right there. Once I have the standard error, I can find the t-stat. What is the t-stat? Let's look at the formula again. This is your statistic. It is the typical statistic. It's your sample difference minus national difference divided by error. It always is. Every statistic, hypothesis statistic looks like this. It's your value minus national value divided by error. The national value you're assuming is 0 because that's your assumption. You're assuming it's 0, so I'm putting a 0 there. It is your differential divided by the error now. It is equal to your error. Well, that's your average minus the other group's average. So that's your differential right there. Think about this. You're comparing that differential, seeing if that difference is that far apart. You can look at it. The blue and red, toward my eyes, look like they're about 8 points apart. Is 8 points apart that big of a difference? Well, it's based on the standard error. That's the key. See, the standard error is how you would jump, and we're roughly a 2-point jump. So when you look at an average of 8 points apart, is that a big deal? Well, let's look at it. And that's a 3.5 t-stat. That is pretty big. That is pretty tough to beat. That is, based on my critical value, my t-stat has gone over the critical value, and so I would reject. I've just completed our research. My statistic is over the critical value, hence I must reject. Again, this number fell into the rejection region. Let me go to my PowerPoint here. 354, and that is not a PowerPoint. I know, it's OneNote. OneNote is a good tool if you're drawing. 3547. Again, it's all about this number right here, green. That number, your t-stat. Where is it in this picture? Well, 354 is way over this bar. 354 is in the rejection region. And so that's what I can say quickly. I'm going to reject H0 because it's in the critical region. Done. Over with. Beautiful. Let me look at my question just to make sure. Is there evidence of a difference? Yeah. There's the evidence of a difference. This is clearly in the rejection region. Now, some of you might not do the critical region, so I want to insert a couple things. I want to insert the p-value because you may be asked to find the p-value instead. To me, it's the check of what I just did. I just showed my t-statistic is in the critical value, in the critical range, which means I reject. Done. Please understand, we are done. 18 minutes into our video. Now, I'm going to run the p-value. That's a secondary approach. It's called a check. Third thing, I'm going to run the Cohen's d, because Cohen's d might give me some insight to see if sample size was an issue. We'll look at that in a second. And then after, maybe, just maybe, I build the 95% confidence interval. And in fact, let me think. If I'm going to build it, let me build it across. So, or actually, that's not true. Let me build it down. 1, 2, 3. Because when I build a confidence interval, I like to make sure I have the error, the lower bound, and the upper bound ready. So, these are the pieces for a full, true hypothesis test. Every one of these steps must be done. Again, the good news is once you write it correctly in Excel, then any question that looks just like this, just got to change the numbers and it updates. Please understand, my critical value needs minor adjustments to make sure it can be updated. It's perfect. That's a great critical value. But if I change my alpha to 0.01, let's say, my critical value did not update. That means that's not going to work for me. This was a 5% one. I'm just asking you, think about pushing yourself. How could I change that formula so it would update with alpha? But you got to be careful on how I got to 0.975. All right, let's get back into the game. So how does one find the p-value? What is the p-value? Oh, back to my picture. Step 4, as I call it. Let me erase that. Step 4 in the hypothesis test. The p-value. So the p-value, what you do is you don't care about alpha in this case. You care about your statistic. Now, again, it is not equal to. Please understand, this was a not equal to test. That's why there's 2 bars. Your p-value is based on your statistic. Your statistic was a 3.547. The p-value is the area, the chances somebody could sample randomly again and find a more extreme sample than yours. What are the odds somebody can repeat your study and get a different answer? So the p-value, bottom line, would be those 2 red regions added together. Now, due to symmetry, this is negative 3.547. Okay, but I'm going to do this so I can always write this code and keep it the same. We need to think about this number. Because even if I got a t statistic, let's say we got a t statistic that was negative, I still want to be able to use it. Okay, I want to use a code that way no matter what number comes in, whether it's negative 3.547 or 3.547, I get the right answer. It's all based on this number. I want to know the red region. Well, since there are 2 bars, the p-value will be 2 times something. 2 times what? Well, the area here, this red area. If you're having troubles with this, you should go back to my videos on the t-distribution and also my videos on just a good old single hypothesis testing. Then you can come back and do the double testing. There should be an order in which you learn. You should learn about the t-distribution, then the 1 sample hypothesis testing with the t-distribution, and then you could do the 2 sample. You should learn it in a proper order. If you've already had that, that's why you're probably here, jumped into this video. So I want to find the red region. Well, I know the blue again. I know the blue. And in fact, when I draw that blue, I shouldn't have drawn it that way. I know I need to do 1 minus because I want to find the area in red. But t.dist finds the blue. That's what I wanted to say. T.dist finds the blue. Okay? T.dist will do the calculus needed to find the blue area. From the blue bar down, it'll find the area. 1 minus then will find the area above by probability rules. All right, if I ever want that extreme area, I'm going to do 1 minus. Now, what goes into the t-dist? Well, the t-dist will take this number right here and put it right there. That's the first number. Then I'll need degrees of freedom, and then, yes, you'll always put a 1 there. The cumulative effect. You wanted to do the integration. You wanted to do the cumulative density function. If you're looking at PMF functions, you're not in this class. So we're going to take the 3.547 and dump it into the t-dist. When you dump it into the t-dist, it'll find the area below. You don't want the area below. That's why the 1 minus. Why the 2? Because there's 2 pictures that are symmetry the same number. The area below this is the area above this, period. The area below here is equal to the area above that, which why I find the red area up here and double it, I'll find both. And so this code now will work for the 3.547. If my t-statistic is negative, I'm going to tweak this formula just a little bit so that way it always works. And we'll show that once we get to Excel. So we're going to bring this formula to Excel. So again, the p-value, it is equal to twice. Why twice? Because there's 2 tails. Now, I need a parenthesis here. I need 1 minus because t.dist does below. It doesn't do above. T.dist will tell me it will take the statistic value. It'll find the area below, but of course it needs degrees of freedom. Well, good news about degrees of freedom. We already got that. And bottom line, it is always true here. It is always a 1. And so that's our answer. Let me go back to the code. Now, I'm going to slightly adjust this so if I see a t-stat's negative next time, I'm not worried. See, this is based on the positive number, which means if I put in the absolute value of this number, I'm guaranteed to be the positive end anyways. That slight little tweak made it so if my t-stat is ever negative, this will still work out perfectly because I based my formula on the upper half, not the bottom half. I based my formula on the upper half. So if this flips around where X bar 1 was lower, let's say, to a 76.4, it would still update and calculate the value out. Of course, I say that, and now I'm looking at this wondering what happened. F1, oh, because that's 76 over 4. That's what happened. A clerical mistake. And that happens. That was a clerical mistake. I wanted 76.4. And bada bing, it updated like I would hope it would have updated. Not the critical value didn't update, so I got to be worried about that. But the T statistic, see, the T statistic updated, and then the P value updated. And this updated properly because of the ABS. If I didn't have the ABS, it would have not updated properly. It would have given me a really wrong number. You have to understand why the ABS is needed. The ABS will take the negative T-stat, change it to the positive end of 1.12, and then we can go from there. So let me bring that back to 86.4. These subtle nuances of Excel that once you get it, save this file and use it, right? That's the great thing about Excel. Once you write it right once, save it, and then change the numbers up, knowing full well you've done a great job of writing the code right, and that's awesome. So, by the way, we need a result. Well, this p-value is 0.00088. 0.00088. Let's get back to the story. My p-value is 0.00088, which is, moved two decimal places, 0.088%. And yes, that is under any alpha anybody's going to give me. Our alpha happened to be 5%, but any alpha you give me. And if you're under alpha, if p-value is under alpha, you reject H0. That's our statement. If your p-value is under alpha, you reject H0. You have found a sample whose probability of being repeated is very, very thin, which means it's statistically significant. Boom. Nice. Step 4 is done. P-value. And it's a check. By the way, if you reject in the rejection region, you better reject here. They both say the same thing. Please. If not, you haven't done enough accuracy to get the right answers. Number 5. Cohen's D. So Cohen's D comes up because people wonder if sample size is the issue. And that sometimes is an issue. You know, how much effect does a sample size have? The effect size, as we call it. Well, we need a formula. The Cohen's D measure is right here. It is the absolute value of the difference divided by the square root of the pooled variance. All right, that's the Cohen's D measure. I'm just trying to make sure I'm in the right. There we go. The Cohen's D measure. And it is the absolute value. That's what those mean. The absolute value of the difference divided by the square root of the pool variance. All right, guess what? This is an Excel command. Yes, you could do this all by hand. Please, you can take a tiny calculator out, get these numbers, plug it in, and get it. That's fine. I like to utilize Excel because once I have the formula written right again, I don't want to touch it again. Absolute value. As I said, ABS, absolute value. Now, it's the absolute value of a fraction, so I need another parentheses for the numerator. The numerator is the difference between the means. Got it, the difference between the means. The denominator is the square root of the pooled variance. The pooled variance is right there, right? SP2, the pooled variance. You got to know your definitions in order to do things properly. And there's my Cohen's D, roughly 1. Now, what does Cohen's D do? Well, let's go back to this now that I've calculated out. You see, what happens is, look at this formula. This formula does not rely on sample size at all. It only relies on averages and the variance of the pooled variance. It doesn't rely on sample size at all. As the T statistic, if you look at the formula for the T statistic, it relied on sample size. The Cohen's D measure doesn't rely on sample size. And because it doesn't rely on sample size, per se, degrees of freedom sort of relies on sample size, so you got to be careful with my phrasing there, right? If you look at the pooled variance. So if you're like, whoa, degrees of freedom is sample size, I agree. There is a little bit of worry about that. But overall, the pooled variance only really deals with the sum of squares, all right? There is a degrees of freedom, but that's a technical thing for bias. And so we get a 1 for the Cohen's D. What does that represent? Well, the great thing about a formula sheet is you have little notes to yourself. If the value is below 0.2, we have an issue with the sample size. If D value is over 0.8, we don't have an issue with the sample size. And that's important. Cohen's D measures significance based on significance. It's based on significance, not sample size. And so what we see here is because this number is over 0.8, because this is greater than 0.8, what this tells me is sample size is no issue. What you have is what people call a large effect size. There's a large effect regardless of the sample. That's really what Cohen's D is measuring. It's saying, let's get rid of the sample size, because some people fight us in research about needing sample size too big, too small, and it messes with your results. Cohen's D is a way to look at that and say, no, based on my Cohen's D, I have a large effect size, which means sample size is no issue. Cool. So, as you notice, I'm plowing through these results. I know I rejected because my statistic was over my critical value. I know I rejected because my p-value was less than alpha. I know I have a large effect size because this is greater than 0.8. These are all the things, once you write it correctly once, now if you change numbers up here, you can watch everything change and just talk about what they mean. Instead of worried about the nuanced calculations, you could talk about what they mean. I do the nuanced calculations because I want you to understand what's involved in each little piece that goes into it. All right, so I want to build a confidence interval. So how does one build a confidence interval? Well, I guess we'll call that step 6. I want a 95% CI. Why 95%? Because I felt like it. So how do I build a confidence interval? Well, to build a confidence interval, it is always two-sided. And what you're looking for is this number. And since that's 95%, that means this is 2.5 on both sides. It's 2.5 on both sides. 95% confidence means it's 2.5 on both sides. I want to find this number. Well, to find this number, a confidence interval is always founded by T dot inverse, and that would be 975, think about it, comma degrees of freedom. Why is it 975? Again, the area below this bar is 975. That's why. Once I have the T value, I can go to my formula sheet, you bet it, to find my confidence interval. My confidence interval for mu is the following. It is, so my confidence interval, it is mu1 minus, not mu, I apologize. You don't know mu, so you can't write those in there. All right, so that's poor on my part. I apologize. That's wrong. Come on, I just want to erase. What is going on? Oh, I do this all the time. If you're clicking erase, you use your pencil, not your clicker. Sorry. It's mean 1 minus mean 2. Because to build a confidence interval, you use your numbers. So that's your numbers. Plus or minus some margin of error. The margin of error will be a T value, which we'll call it T star. This is T star. Your critical value times, as you notice, the standard error in our formula. The standard error being S sub M1 minus M2. That's your confidence interval. Good news, you had everything except for this number. You had everything. You have M1 minus M2. You can look that up. You have S, the standard error. We already had that. We had to calculate that out. The only thing you were missing was T star. Well, T star is this command. So in Excel, I would, to find the error, as I call it, you would need T dot inverse of 0.975, comma, degrees of freedom. Good news, we have our degrees of freedom, right, guys? Times, let's make sure I get that formula right. So the error is the back end of the formula always. T times S sub M minus 1 minus 2. That is called the standard error. Boom, there's the error. Got it. Now, how do you find the confidence interval? Well, the confidence interval will be based on the mean differential minus the error and the mean differential plus the error. And so I can say with 95% confidence, the true differential between the two groups is somewhere between 3.29 points and 11.91 points. Why would I want a confidence interval? Well, once I have everything done, now we can summarize. Now that everything's been done for you, and this is the cool thing, now all I got to do is go up here and have fun, change these numbers for my next question, and this all changes with it. So I don't ever have to worry about calculating these out again. That's why I would pause the video and make sure that each and every one of these is written correctly. Because once they're written correctly once, then you just got to change the numbers up here. It's like, oh, I made a mistake. I didn't want 1550. I meant 1,000. No problem. Boom. And everything adjusts. And that's awesome. No work, no muss. It is 1550, so I want to put that back. All right. So here's my answers. Now, I'm pretending I just typed all this in. Let's make this a 5-minute question. I just spent 36 minutes explaining to you what's going on. What you do, you type this in. Got it. And thankfully, the computer knows how to find degrees of freedom. Critical value, please. We still have to update. We haven't changed that off of 5%. We got to figure out how to fix that. If we want to change alpha, what happens to this? How to fix that. That's left for you to investigate. So, now, what are we doing here? We're creating a statistic. All right, we're creating a statistic of measurement based on 2 samples. So we're pooling the spread together. That's what we're doing here when we're doing this. We're pooling the variances, and we're finding the average difference based on that pooled variance. That's that 214. That's the average point difference right there. Standard error is always an average distance. In this case, it's the average difference between the 2 groups is a 2.14. That's the pooled variance, and that led me to the standard error. The t-statistic is based on that. My average, according to my sample, is roughly 8 points. But because the spread is roughly 2 points, that's why the t-stat is 3.54. Now, that's still significant because the p-value of that statistic, that is the odds of repeating this study and finding a sample more extreme, is very thin. The way I look at it is this number less than alpha? If it is, then you reject. Less than alpha, then you reject H naught. And I know I wrote that incorrectly. Less than alpha. Then we reject H naught. That's true. That's very important. T-stat, is this more than the critical value? Then we reject H naught. These are kind of questions right there. Are you more than the critical value? Then you reject. If you're not, then you do not reject. Is this number less than alpha? No, then you do not reject. That's really what it comes down to. Cohen's D. What is Cohen's D? Is it more than 0.8? Then we have a large effect size. See, all of these will be reported in your final answer. Every stinking one of these. You'll report my t-statistic is 3.55. That t-statistic has a p-value of 0.0881%. The Cohen's D is 1, which means we have a large effect size. Bottom line, because we rejected, we had to find the true differential. The true differential, if this study was done over and over in a large mass, the true differential, I have 95% confidence that the true populational difference would be between 3.29 and 11.91 points. Awesome. All right, guys. We're going to speed through the next one. I'm going to actually populate the answer and then unpause the screen. But I want you to pause right now and try to figure out how I'm going to take all this work. I'm just going to copy and paste all that work right into here and change it. But of course, let's look at this question. Is there evidence of a significant increase? Uh-oh, that's a one-tailed test. So I got to figure out what does that adjust up here when it's a one-tailed test. Also, level of significance 10%. And also another little note. They gave me the standard deviation. Uh-oh. How do you go from standard deviation to sum of squares like I've done? How do you go from standard deviation to sum of squares? So I'm going to have to adjust a little bit because I have a standard deviation. And I'm going to have to figure out how to deal with a one-sided hypothesis test because this is not a two-sided test. We'll be back. You try it out first. All right, guys, welcome back. So I have completed the problem, and now I just want to walk you through what I've done to change because of the key pieces of information. What key pieces of information? Well, is there evidence? It means a hypothesis test. First of all, it's one-sided, a significant increase, so it's right-sided. I call it the positive tail. When we're looking at do people that come out with a CFA, do they earn a lot more than an MBA? And so that we're looking at, is there a true increase in average salary for a CFA from an MBA at a 10% level of significance? Actually, I got to make that 10%. 0.1. All right, so there's 10%. All right, so what do we do? Let's go through our process, and let's go through it pretty quickly. You should pause it as needed. Since our 6th example, I want to move along. First of all, you need your null, you need your alternative, and you want your alpha. Alpha was 10%, so 0.1. Your null is the difference right now between the 2 degrees is 0. You're trying to show that there is clearly an increase in one of the degrees. So I got to change that to less than or equal to match the opposite. See, the alternative is always in the question. This is always the question. This is what you're investigating. This is the ITE, what you're investigating. Is there evidence of an increase in the difference? Notice the increase to greater than 0. All right. Is there evidence of an increase? You could also write this by saying mu1 is greater than mu2. That's fine too. I believe the average in one group is greater than the average in the other group. Just got to be very clear what average you're looking at, which is 1 and which is 2. So when you type these in, you get these correct. So my question, the CFA title will be group 1 because that's the one I believe are going to beat the MBA titles. So that's group 1 is the CFA, group 2 is the MBAs. I believe there's an increase in salary of the CFA over the MBA. They have a greater salary. And so a no would be, no, they don't. They don't really. I believe they do, but the natural would be, no, there's no difference. I believe looking at data, there is truly a difference. So how do we go through this? Same exact process though. I want to make that clear. Step 1 was that. Step 2, critical value. So critical value is one-tailed. How do I know? It was a increase. Increase means the positive side. All right. And because I have my alpha, all of alpha goes to the extreme side. Alpha was 0.1, so this is 0.1. There are not 2 bars, so do not divide by 2. All right. Do not divide by 2. This is a one-tailed test. So you keep alpha at everything outside of that. So how do I find a critical value? You use your T inverse. So the T dot inverse of, so I need the area below. Think about the area below, 90%. Comma degrees of freedom. Booyah. T dot inverse will find you the critical value. So that's what I typed into Excel. In Excel for critical value, and in fact I automated because I realized since alpha is always going to be the area above, right? Alpha it's a one-tailed test to the positive side. So alpha will always be the area above. Since it's always the area above, then my T dot inverse will always be 1 minus alpha. Huh? Clever of me, right? So I've now automated. So if I change that to 0.5, I will get my new critical value. It was 10%, so let me change it back. Now that I did it here, maybe that wink wink gave you a hint to how you could update this one a little bit. Careful for that. All right. Anyways, so alpha is 0.1. And so notice the critical value went to 1.29. That's our critical value. Excellent. Critical value is 1.29. And there's only one critical value. There's only one bar right there. We either exceed the bar and reject H0, or we do not reject H0. So how do you determine? You go to step 3. You crank out your T statistic. Good news. T statistic doesn't change except for the fact to get to this number, you need sum of squares. The problem is they didn't give you sum of squares. They gave you the standard deviation. So I had to look this up on our formula sheet. You may pause if you need to. How do you go from variance to sum of squares? I had to figure out how to go from standard deviation, to sum of squares. And that's my formula for going from the sum of squares to standard deviation. So S equals radical SS over n minus 1. So I got to solve for sum of squares. Algebra would say you square both sides. So S squared equals sum of squares divided by n minus 1. Then what would I do next to solve for sum of squares? I'd cross multiply. So sum of squares will be equal to S squared times n minus 1. All right, that's it. And that's what I'm going to write in Excel for my sum of squares. For sum of squareds, I'll take S squared times n minus 1, where S is the standard deviation of the sample. So I wrote into my problem standard deviations from the question. All right, and so now the formula would be S squared, standard deviation squared, times, and please put in parentheses, n minus 1, degrees of freedom, right? N minus 1. And there's n, so n minus 1. Same thing over here. This would be standard deviation squared times, and that's very important, degrees of freedom, n minus 1. Because that's the formula I was able to concoct when I utilize this formula backwards. To get rid of a square root, you square both sides and you cross multiply. Awesome. Once I have that written, now my problem, for this one, now that I have the standard deviation, that'll easily adjust the sum of squares for me. So now I have a nice example of here that works with the sum of squares. I have a nice example down here that works with standard deviations. Two practical problems you might run across. Once you have that, then the t-stat's no big deal. There's your t-statistic. 0.9969, might as well say 1. My t-statistic is 1. So my t-stat is 1. Well, does my t-stat fall in my critical region? Well, my critical region is 1 to 9. The answer is no. 1, all right? A t of 1 does not beat a t of 1.29. So it does not fall in the rejection region. All right, so my t-stat, is it more than CV? No. Is it more than a critical value? No. So DNR H naught. Do not reject H naught. Pretty simple. I wanted my t-stat to be bigger than my critical value. It is not. So no. I do not reject H naught. I do not believe there's a significant difference. I'm done here. I don't believe there's a significant difference between the two. But we'll move on with our analysis. By the way, the Cohen's D is still good. The Cohen's D really had nothing to do. Well, once I upgraded the SS1 to be accurate, then I know the Cohen's D measure is accurate. And remember, going back to our formula sheet, this is why you have all these nuances with you, ready to go, so you can look at it. Going back to our formula sheet under the Cohen's D information, if the D value is below 0.2, we have an issue with sample size. Interesting. This is less than 0.2. We have a issue with sample size. That means we have a small effect size. This is something we need to look into then. We definitely have a small effect size. So sample size could be an issue, and we should investigate whether that means we should redo the study or not. All right? We definitely did not reject, but there is a potential of an issue because of a small effect size. Okay, careful of that, people. All right, what do we got? P-value. Is that correct? Well, the P-value, we did the critical value. We got the t-statistic, and that told me DNR, H naught, because my test statistic was not in the critical region. 4, P-value. Well, the p-value is based on the picture. This case, 1 bar, please. Your one statistic is 1. That's funny. That's your statistic, right? That's your up here, and I'm going to be using the most accurate number in Excel, the 0.99. But let's say it's 1. The p-value, notice 1 bar, and we're doing a more than test. So the p-value would be the probability of finding something more extreme. What is that p-value? Well, to find a p-value, you just got to understand, how do I find that red area? That's calculus. You would find an integral and calculate it out. In this case, we're going to let Excel do that. See, t.dist will give you the area below any bar. So whatever number you put in, 1, it'll find it. You just need to tell it degrees of freedom to know what curve and to do the integration. So that's the one that matches that. But that finds the area below. When you do t.dist, it does the area below. You don't want the area above, and that's why it's 1 minus. It's 1 minus because that's the red. If you just did t.dist, it'd give you the area below. That's just something you got to learn. Please notice, I'm not multiplying by 2. I'm not. I don't have a lower edge. This is a one-tailed test. I'm only caring about an increase, not a difference from. That's why I'm not multiplying by 2. All right, so got to adjust our p-value. And in fact, I already did. It's 1 minus. Beautiful. Notice your p-value. Is it less than alpha? The answer is no. So DNR. Notice that number is 16%. Your p-value is 16%. A pretty good chance somebody can repeat your study, which means you're not statistically significantly useful. So we do not reject here because my t-stat is not in the critical region, right? 1 doesn't get into the critical region. My p-value is above alpha. That's a problem. My p-value is above alpha. Big p-values means we do not reject. My Cohen's d is an issue. Oh, and let's look at the confidence interval. By the way, good news. Confidence interval doesn't have to change. I'm building a 95%, and that still would be the instructions for 95%. So that's good news. This is automatically updated. No issues. Notice the confidence interval. I am 95% confident the true differential would be between these two numbers. Now, normally people would say, who cares? I care because there's one number between them that makes it all come true. It's a third rejection. 0 is between these two numbers. To go from negative to positive, you needed a 0. And if 0 is between the two numbers, that means there's a potential that the true average is 0. Right? If 0 is in the confidence interval, that means there's a potential possibility that 0 is the true differential. And if 0 is the true differential, that means potentially the true differential. That means there's no difference between the two. That's our third check. If 0 is in this interval, then that means the difference between them is not significant. All right? So 3 checks. The t-stat is not bigger than a critical value, so I don't reject. My p-value is bigger than alpha, so I don't reject. Oh, by the way, 0's in this interval, so I don't reject. All 3 times I do not reject H0. What does that mean? I find no evidence that there's a difference in salaries. Is there an increase in salary? No. I find no evidence of the increase in salary, period. Excellent. All right, guys, thank you for watching this video. My next video will deal with a data set, and I'll show you when you have a data set how quick and easily Excel does all the numbers for you, okay? Excel is going to calculate all these numbers for you and then dump it all in nicely for you, and that's awesome. All right, guys, thank you for watching this video.